And we're back. This is Chapter 17, Thermochemistry. This is P-Dog, and here is our lecture for the unit. Some things I want you to keep in mind. There are some questions over here on the side, and you'll see comments throughout the notes. Please keep those in mind and try to answer them as we go through our lecture today. So we're going to start with 17.1, the flow of energy, heat, and work. Energy transformations is how energy moves from place to another. And energy is the capacity for either doing work or supplying heat. Now, we can only detect energy because of its effects. We've talked about this in class before with potential energy, when things are cringeworthy. So if we had a rubber band stretched and pointed at you, or if you had a heavy object over a body part of yours, then that would be cringeworthy. That would have you worried about the energy that the object has directed at you. We've also talked about kinetic energy, and that's how things move. It's the speed of how things move, and that is directly related to the temperature of objects and how they interact with each other. And we've also talked about the flow of heat when it comes to endothermic and exothermic reactions. And so keep those in mind when we're talking about energy. All of these are examples of our energy. When we talk about it in chemistry, however, it's called thermochemistry. It is the study of energy changes that occur during chemical reactions and changes of state. And I should probably fix that here. During changes of state, changes of state. Okay, so when it changes from a liquid to a solid, or solid to a liquid, or liquid to gas, or something like that, it's a change of state. The energy stored in chemical bonds is called chemical potential energy. And all chemical bonds have some amount of energy in them. Breaking them may release more energy than it takes to break, or might take more energy to break those bonds than what they release. During reactions, one substance is transformed into another substance, and there is always a different chemical potential energy. Maybe just a slight difference, or maybe a huge difference, and that's what we're going to be measuring and paying attention to in this unit. Now, we buy gas for its potential energy. Okay, gas has chemical potential energy in it, and that's what we purchase it for. And what it does, it propels the car, okay, which is the energy doing work. But the engine also gets really hot, and the heat coming off of the engine is also coming from the gasoline. Okay, not to mention the electricity that's running all of the gadgets in your car, the radio, your lights, if you're charging your iPod or whatever, you're charging your phone in your car, that also is all energy coming from the gasoline, because there's something called an alternator, which takes the spinning action of your engine and runs a generator, which creates current for your electrical devices. But all of these, or the ones that we actually pay more attention to, is heat. And heat is the variable Q. Q actually stands for quantity of heat. It's so very creatively named. Sort of disappointing, but that is what the Q stands for. Heat, then, is energy that transfers because of a difference in the temperature between two objects. Now, heat always flows from a warmer object to a cooler object. In fact, it's the only way that makes sense. If you try to imagine the opposite being true, imagine putting an ice cube into a cup of coffee. And if heat always flowed from a cooler object to a warmer object, then the ice cube would start to get colder, and the water and the boiling water would start to get hotter. So you would have this super cold ice cube in the middle of boiling water. It makes no sense. The only way it can make sense is if you have heat flowing from a warmer object to a cooler object. And this flow happens until the objects are in thermal equilibrium. This thermal equilibrium just means, and I don't have a whole lot of room here, so we'll write over here on the side, that two objects in contact with each other are at the same temperature. Two objects in contact will be at the same temperature. That is thermal equilibrium. All right? Now, when we examine this, either heat is going to flow into an object or out of an object. And we call these exothermic and endothermic processes. And we've discussed these before. Chemical reactions generally involve either a release or an absorption of heat. And if it releases heat, then it is exothermic. And if it is absorption of heat, then it is endothermic. So we have the release of energy is exothermic, and the absorption of heat is endothermic. Okay. Thermochemistry then studies the flow of heat between a system and its surroundings. And we need to do this because of the law of conservation of energy. Because of the law of conservation of energy, all of the energy must be accounted for. There should be a comma there. All right, but I do want you to think, what is a system in this context? What do you think constitutes a system when we're talking about the flow of heat between the system and its surroundings? I am not going to tell you this. I'm going to leave this to you guys. This is an independent study, or let's call it independent research. Independent research topic. It should only take a minute to find out what we're talking about with system. Okay. So that brings us to our next page. All right, here comes our next page. So, in thermochemistry then, the heat flow is from the point of view of the system. In an endothermic process, the system gains heat as the surroundings cool down. So the system itself will bring heat in from the outside, and the surroundings on the outside cool it down. In an exothermic process, the system loses heat. It gives up heat to the surroundings. It heats up the surroundings. Okay, so we have units for measuring heat flow. Heat flow is measured in two common units. It's the calorie and the joule. Okay, and calorie comes from the Latin for calor, which means heat. Is direct translation in Spanish as well. Okay, so the calorie then is the quantity of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. That's it. If you have 1 gram of water, okay, and you want it to go up by 1 degree, you add 1 calorie of heat. It's sort of similar to the density of water is 1 gram per milliliter. It's the same idea, it's the same kind of definition. Okay, however, a food calorie is actually 1,000 of those, and so you'll see on all of your food packaging. So if you look at the nutritional facts of any kind of food, in fact, any kind of food that's processed, is expected to have labeling that includes the nutritional facts. So I decided to pull up one of a Big Mac to show you about the calories on a Big Mac. And if you look close, right, in fact, let's expand this a little bit. This is taken from foodfactsinfo.blog or /blog. If you look right here, here are the calories. And if you notice, right there, that big C, in fact, if you look on any other nutritional fact, that calories will always be capital right there. They put it there, it's not just because it's the first thing listed on the line like these guys are. It's a capital. And these are all listed the same way because they want to make it look the same way. This is actually, let's zoom in a little bit more right here. If we zoom in more, okay, that 560 right there is actually 560,000 little calories. The big C for a calorie is 1,000 little calories. So, if I take this off, okay, food companies want you to eat their food, and they don't want you to think about the calories, and so they disguise it by just using a capital letter rather than calling it what it truly is, which is a kilocalorie. All right. Now we tend to not use calories in our calculations. They're a little bit easier to use when we do some calorimetry later on, but we're going to eventually, what we use for our thermochemistry is called the joule, and this is the mechanical equivalent. This is the unit for the mechanical equivalent, and that's just horribly ugly. So let's see if I can just type it out here. It is the mechanical equivalent to heat. Excellent. Okay, it is the mechanical equivalent to heat. That this 4.184 joules, each joule actually equals the force of 1 meter, of 1 newton over a distance of 1 meter. So this 1 newton times 1 meter is 1 joule. And 1 calorie equals 4.184 joules. These units will make more sense when you take physics, but it took many years to actually to figure out what this relationship was, and it was figured out by a man named James Watt, who was able to come up with the mechanical equivalent to heat. Okay, which brings us to heat capacity. The heat capacity of an object depends on both its mass and chemical composition. This really is just how much heat is in something. Okay, remember our temperature is based on the absolute temperature scale. So if we do this, with kelvins, then we can actually measure the amount of heat an object has based on its mass, and we'll get to, and its heat capacity. Okay, the greater the mass of an object, the greater its heat capacity. The greater the mass of the object, the greater its heat capacity. So if you think about it on a larger scale, a swimming pool in winter will have enough heat to melt more ice than an almost boiling cup of coffee. And why is that? Because it's not about the temperature. It's about the amount of heat. It is about the heat capacity. That a swimming pool holds more heat in its water above freezing, holds more heat above freezing than a boiling cup of coffee. That's why it's able to do that. Okay. And we can start measuring this sort of stuff by using what's called the specific heat. The specific heat is given by the variable C. Okay, and it is the amount of heat it takes to raise the temperature of 1 gram of a substance 1 degree Celsius. Okay, and they are on, you'll see those on page 508, table 17.1, which I happen to have right here. Okay, and here's your that table 17.1 of your specific heats. Let's scroll down here a little bit. Okay, where if you look at this is joules per gram degree Celsius, or calories per gram degree Celsius. If you'll notice, water is 1 calorie per gram degree Celsius. This is the definition. This is how we came up with the calorie, and then we converted it over to the mechanical equivalent with these. And we actually use these values more frequently. Water is exceedingly high. It's almost double everything else on this list, which is one of the cool properties of water, that it has such a high specific heat. And the small changes in this will cause large changes in other things. But here is our list of specific heats of other substances. Notice how the metals down here are very low, because they conduct heat very well. Where these guys, these are nonmetals, and these conduct heat at a very high temperature. These don't conduct heat very well. Okay, and we can measure this using the concept of, okay, so we can measure the amount of heat flow in or out of a system, and we use this equation that is mc delta T. Q equals mc delta T, which, by the way, is my wrapper name. That is P-Dog's wrapper name. P-Dog is not the wrapper name. P-Dog is the science teacher name. Okay, but my wrapper name, my pseudonym, is mc delta T. And right, so on to the next page, where we do where Q of the Q equals mc delta T. Remember, we have Q equals mc delta T. Q equals mc delta T is the heat exchanged, the mass is our mass in grams, m is mass in grams, and delta T is the change in temperature. Delta T is always a final minus an initial condition. Remember, delta means final value minus initial value. It always means that in all of your science and math experience. Delta means final minus initial. Okay. So here's our example. The temperature of a 95.4 gram piece of copper increases from 25 degrees Celsius to 48 degrees Celsius, and the copper absorbs 849 joules of heat. What is the specific heat of copper? Well, we're going to use this equation, Q equals mc delta T, but we want to find C. So we're going to convert this equation to actually give us C equals, okay, it'll be Q over m times delta T when we solve for C. Okay, and then we start plugging stuff in. So we know that Q, let's erase this up here, that our Q is going to be, is our 849 joules of heat. That's our Q, 849 joules. Okay, our mass of our sample is 95.4 grams, and our temperature, or our change in temperature, is going to equal 48 degrees Celsius minus 25 degrees Celsius. And it has to be in that order, because if this were to cool off, then we would have a negative heat value, and we would be able to, okay, and we might actually be losing energy. So we take these values and we plug them into our C equation, 849 over 95.4 times that difference right there, which winds up being 23 degrees. And we get 0.387 joules per gram degree Celsius. And that is how we do a Q equals MCT calculation. So that is the end of 17.1. 17.2 is next. And this is P-Dog signing off, and we'll see you guys next time.